Electrochemical oxidation of liquid metals creates snowflake-like liquid metal fractal shapes. The newest class of instabilities in liquid metals is the oxidation-mediated. These instabilities are unexpected due to large interfacial tension of metals. Interfacial tension is defined as the work that must be expended to increase the size of the interface between the two adjacent phases, which do not mix completely with one another. An example of the liquid metal used is eutic gallium-indium, which is a mix of metals that at room temperature and offers a low toxicity alternative to mercury. This apparatus consists of a shallow dish filled with 1 mole of sodium hydroxide solution to provide an active dissolution of the oxide layer and increase the ionic strength relative to deionized water. The outer rim of the apparatus contains a copper ring electrode centered around the liquid metal droplet placed on the central electrode. In the study, 2 parameters were varied: the volume of the droplet and the applied potential E. How it works. The metal's surface becomes oxidized, which lowers its surface tension in the same way that soap lowers the tension in water. As the gravity spreads the metal out into a disc shape, disturbances on the surface result in a dramatic shape change, and the liquid metal alloy is broken into individual petals. As they grow, the petals break up and branch out more, creating a fractal pattern. The largest liquid metal snowflake is around 20 times the size of the original droplet and can form in less than half a minute. However, researchers only found that this effect works for a narrow voltage range of around 2 volts. At lower voltages, the droplet surface doesn't oxidize enough to disturb the droplet, therefore no fractal pattern forms. If the voltages are too high, then the surface oxide layer grows too thick and doesn't allow the droplet to spread and break up, therefore no fractal pattern forms. The video shows what happens when either voltage is too high or too low. The oxide layer will inhibit the spreading of the metal. This is due to an electrochemical oxidation generating compression interfacing forces that oppose the tensile force at the liquid interface. This means that the surface oxide layer will induce instabilities and provide a physical barrier that halts the instabilities at larger positive potentials. Liquid metals have many applications as a result of their optical, electrical, and thermal properties. However, with the largest surface tension of any room temperature fluid, they are very difficult to spread and unlikely to be a candidate to undergo the instability. The patterning techniques organize into 4 categories: patterning enabled by biolithography, injection, subtractive techniques, and additive techniques. Many of these approaches make use of the surface of gallium. Differences between oxidation-mediated and other types of fingering. One key difference is the measured fractional dimension is smaller than the measured value for viscous. Viscous also tends to occur when the fluid is being injected at constant flux or pressure, and the instabilities occur for an unconfined constant volume of a droplet. Viscous fingering occurs in less viscous of the 2 fluids, whereas oxidation-mediated will be twice as viscous as the surrounding liquid. In the oxidation-mediated fingering in the Liquid Metal Journal article, the paper identified the mechanisms between the instability as arising due to interfacial tension, gravity, and oxidative stress.